Hopefully everybody can see my screen.
Yes, everything fine.
Yes, awesome. Okay, thank you very much. So I'm going to talk about ordinal partition networks, and this work has been performed jointly with Thomas Temler and Michael Small while I was doing my PhD at UWA. So it is a concept based on the idea of applying a transformation to a time series and generating a network to investigate instead of the original time series. So let's take things, let's start from the measurements. Usually you have experimentally, we have a time series that is some observable of the state of a multi-dimensional assumed deterministic dynamical system. And so I'm going to assume for this methodology that the time series is either a state variable or a nonlinear monotonic transformation thereof. Now, this method can be applied to both discrete time and continuous time systems. So we have the usual separation, iterated maps, and solutions to differential equations. Okay, so we're particularly interested in ergodic chaotic systems. Definition of chaos, we require three essential properties. So one of them is full mixing. The other is sensitive dependence on initial conditions. And the third is that periodic orbits are dense in the attractor in the same manner that, let's say, rational numbers are dense within the set of real numbers. I'm sort of briefly going over these fundamentals in order to move on to the actual method and spend more time on the results. There are a few quantities that are dynamically invariant and therefore hold quite a bit of significance. So one of them is the natural measure, essentially the occupation probability of each state. Lyapunov exponents measure the sensitivity to initial conditions, so they are basically a quantification of the exponential separation rate of states that are very proximate initially. Fractal dimensions is another very common tool, KS or metric entropy, and then topological entropy. I'm going to focus quite a bit on Lyapunov exponents and topological entropy as applications of this methodology today. So two well-studied example systems are the logistic map. It's a one-dimensional discrete map. It's expansive in its dynamics. And here you see a time series from the regime where the growth rate parameter R is equal to 4. The other very well-known system that I base my examples on is the Lorentz system. So this is the three-dimensional chaotic flow. So let's begin with what ordinal patterns are and what this kind of time series transform represents. So we can think of the time series as a trajectory part of an orbit, the orbit being all the state space points that are visited. So sort of the past and the future from space. And we can apply Takin's delay embedding method in order to reconstruct the state space. And this would be done by choosing an embedding dimension and embedding lag. And essentially the result is a high dimensional image state space that presumably holds the same topological dynamical properties as the original. Now, ordinal patterns are essentially permutations of a certain length. So here, for example, I have all 6 possible permutations of order 3. They can be represented in more than one. Wave cycle notation being one example. In general, if you have a time series, just as the one displayed on the bottom right figure, this time series is segmented into windows of fixed length, equal length, and literally the visual pattern that one can observe may be encoded using the set of permutations of specified length 3 in this case, or sorry, 4 in this case, in the bottom right figure. And one can record statistics thereof, but also the temporal sequence, so which patterns follows which. And this example is actually taken from the Z equals 27 Poincare cross-section in the Lorentz system. So essentially we have an alphabet of elementary symbols, as I say, permutations of order n. And we cover the image state space that was generated by Taken's delay embedding method, using a finite collection of connected sets of non-empty interior. So essentially we have two properties that the image state space must be covered by all these regions, and that the interior is not empty. This here is essentially the formal definition of an ordinal pattern. So one way to think about it is within each window, within each segment of the time series, points can be ordered according to the values, and essentially the chronological index sequence is the permutation that represents that particular ordering. Through this process, one will generate a symbolic sequence, so-called itinerary. And I'm going to show some examples very shortly, but this sequence is essentially all symbols that represent the original trajectory as it is moving throughout state space, but using labels, using symbols instead of actual values. So as an example, let's take the logistic map. And here we essentially have, start from the point x1, let's say, and move it forward in time according to the logistic equation rule, and observe what happens to all forward iterates in the sense, where do they lie with respect to the diagonal x equals y line. And so we start in the blue region, and the second point is still in the blue region, but then the third point is here in the red region, etc. So essentially, the encoding, in this case, the ordinal pattern should be of length 2. And the encoding represents this state space motion within the partition, within the partition of the image state space. So if the image state space is of length 2, we have this picture here, but let's say we use a pattern length equal to 3. So we segment the time series into slightly longer windows. In this case, the mapping, the image state space lives in 3-dimensional space. And again, we can record how this trajectory moves depending on which region it goes into. As you can see, in this case, the logistic trajectory actually moves into 5 regions and never visits the region shown in purple. This is dictated by deterministic constraints. I'm going to talk about it in a sec. But essentially, the view I would like us to have of an ordinal partition is this. We have an image state space of dimension 2, 3, 4, etc. And it can be fully partitioned into m factorial elements. So 2 in the previous case, 6 in this case, or let's say 24 in 4-dimensional. In the 4-dimensional case, there is a common boundary between all these regions that would be the diagonal line, x equals y equals z, etc. And we observe how the trajectory moves in this space according to the embedded vectors, according to the embedding vectors generated by the Taken's method, and then record statistics on top of that. Now, we have a 1-dimensional trajectory, let's say the logistic map. We map it to 3-dimensional space, observe something about symbolic dynamics. What is it actually represent in terms of the original 1D state space? So if we map back, if we project these 6 regions into, well, the 5 visited regions back into the original state space of the logistic map, so the interval 0, 1. And if we plot points that are mapped to each different region by different color, we observe this partition of the one-dimensional interval. So essentially, the points that were mapped to the permutation 3, 1, 2 form the largest partition element. And you also see that there are 5 regions because the sixth region, 3 to 1, was never visited. This is dictated by the 3 iterates of the logistic map. So the first iterate, the second one here with the one sort of peak, and the third iterate with the 2 peaks. It is easy to notice that there is no region whereby the third iterate is larger than the second iterate and larger than the first. This is why the constraint exists. It is dependent on the system itself. So as I mentioned, we can record statistics, we can record the empirical distribution of ordinal patterns, and we can also apply the counting measure on the space of ordered pairs of patterns. Essentially, this represents sort of one step forward time transitions in this symbolic dynamic framework. So there are patterns that are actually observed. The set of distinct occurring patterns is called admissible patterns. But as we saw, there are patterns that are never observed. The corresponding regions in the ordinal partition are essentially never visited. They're called forbidden. And there are type 1, type 2 errors. So we can identify false admissible patterns if the time delay used is larger than 1. This is why we specify in our parameter selection time delay equals to 1, specifically to avoid these aliasing effect. There can also be type 2 errors in the sense we identify false forbidden patterns. So patterns that are not observed, but just because the trajectory that we have is too short. So sample size also plays a role in accurately representing the original dynamics in terms of ordinal symbolic dynamics. So from all this information, one can actually form a network. And the network is just essentially each region in the ordinal partition is represented by a node, and then links are formed according to the temporal sequence dictated by the time series. So consecutive symbols in the itinerary will be viewed in the network as 2 nodes that are linked by a directed link. And we can form the directed multigraph in the sense that each link will be assigned a number, a positive integer. This number will, represent the frequency of this transition within the symbolic itinerary. We can also transform this matrix into a right stochastic matrix by normalizing over all outgoing neighbors. This would be the transition matrix that is sort of typical of Markov processes. And we also have the connectivity graph. So if we just transform every entry in the transition matrix to unity, every non-zero entry, then we just have a view of how the different regions in the ordinal partition are connected, but without any kind of weights. One thing to mention is that these directed multigraphs are very natural tools for representing a Markovian framework. In our case, we have a finite memory Markov process. The reason goes back to how we count patterns. So again, looking at the bottom right figure, the different windows, the green, orange, and purple one, essentially do not overlap in more than 1 points. The number of points that these windows do not overlap is represented by W. That's called the slide lag, is one of the parameters. Through some sensitivity analysis, we have determined that selecting W equals 1, so consecutive patterns only differing by a single point, is optimal, which means that we have a finite memory Markov process, since the symbols that result out of all this symbolization are based on overlapping segments. Moving back to the network. So using the logistic map in 2 different parameter regimes, one being a 4 periodic regime the other being the usual R equals 4 chaotic regime, we see that the resulting networks for pattern length of 3 points are quite different. Well, one of the two networks, the one corresponding to the periodic regime, is cyclic, as expected. The other one is more complicated and allows for much more complicated random walks stemming from it. If we look at the Lorentz system, I have plotted two networks that correspond to the Z equals 27 Poincare map again, and they are generated using M equals 4 and M equals at the top and M equals 7 at the bottom. So one can see that the network visualization, in this case a spring embedding based visualization, does visually bring similarities to mind between the network and the original attractor. So hopefully this kind of representation and network properties or network metrics applied to this topology can give us back and produce accurate estimations of dynamical invariance. Now, very briefly moving on the sensitivity analysis, we have done quite a bit of experimentation on an ensemble of systems, both discrete and continuous time, and we have looked at sample size of time series length and how the network changes. We have looked at the pattern length as well, and also time delay in the slide lag. In terms of the latter two, time delay of 1 point and slide lag again of 1 point seems to be optimal. In addition, it produces the most number of symbols that can be extracted from a given time series. And now moving on to the interesting bit, applications. So one can look at these networks from various perspectives. One is looking at clustering coefficient of each individual node in the Watt-Strogatz type of definition. Another is looking at all the K cycles, so cyclic paths that start from a node and end in the same node, and also some other measures that I'm going to move into a bit later because they're based on ergodic theoretic ideas. But let's start from the purely topological measures. So cycles and detecting path. This is done very easily, by the way, because the adjacency matrix, one can look at its powers. These powers represent the number of walks from a node to another. And if we look at the diagonal, that means we are essentially focusing on 2 cycles. And we have applied it to the Lorentz trajectory that I showed earlier. So in this figure, we observe the frequency of the time series points that are mapped to those specific nodes in the network that belong to cycles. So essentially we detect cycles, we look at which nodes are involved in these cycles and which links, and then kind of map back to the X component, so the first of the 3 components of the trajectory. Since we're doing it on the Poincare map, we have actually 2 components. We map it back and we look at the histogram. And the hypothesis here is that peaks essentially correspond to either fixed points or periodic orbits, unstable periodic orbits. Now, this is confirmed by the results shown later. So the second thing is do something
3
similar.
minutes, yeah.
Okay, cool. Do something similar on the Poincare map itself. And here, what I did was I picked some of these points that were mapped. In there, for example, in this case, we only had 2 points being mapped on this particular node. And once you integrate them, you see that they actually lie very, very close to an unstable periodic orbit. Next example is a topological entropy, which we calculate via the natural logarithm of the spectral radius, so the largest magnitude eigenvalue of the connectivity matrix. So I applied this again here. It's the logistic trajectory, and for various time series increasingly larger. What we observe is a scaling region, which elongates as we increase the pattern length. By the way, increasing the pattern length essentially means that the partition is becoming finer because recall that they're n factorial elements. And you see that for a rather long 10 million point time series, this scaling region is quite long, akin to traditional embedding practice. And the accurate value is the actual value, log 2 is shown in red here. Same thing, same definition of topological, ordinal topological entropy applied to various regimes in the logistic map. And you can actually see that bifurcations are distinctly sort of observed just by looking at the metric that we calculate. Then another ergodic theory-based definition, this one applied on the transition matrix rather than the connectivity matrix. And we have a formula for estimating the sum of positively abnormal exponents. So applying it to one-dimensional expansive dynamics, the logistic map is here, but all the others are very similar. Some are like the tent map and the dyadic map in the particular parameter regimes topologically equivalent to the logistic map, and we see that we have actually accurate behavior and much better behavior than traditional measures like the permutation entropy or sorting entropy originally introduced by Van den Boom. Then again, in similar manner, looking at the bifurcations, the orbit diagram of the logistic map. And in this case, we have calculated the level of exponent using Osledek's formula on ergodic systems. And we see that the ordinal sum of level of exponents is actually produces rather accurate values for most of the parameter choices. And so are very, very close to the real level of exponent represented by the red solid line. We do notice some discrepancies, especially close to bifurcation points. So when we are on bifurcation points, this method seems to have some issues because of the peculiarities of the time of the input time series. So in conclusion, ordinal partition networks are a way to represent a system thought to have generated a given time series. The time series that we use are scalar, and any projection of multidimensional systems suffices to generate a very similar result and produce accurate estimations of certain important dynamical invariants like topological entropy or sum of positively abnormal exponents, even for very small finite values of m, so the pattern length, because there are, in certain special systems, there are theoretical arguments about convergence to metric entropy or such quantities when m tends to infinity. But what we see via these numerical experiments is that one can obtain relatively good estimates for very low values of the pattern length. And I think I'll stop here.
Thank you, Kostas. Very interesting. And we have 1 minute and 30 seconds left for questions. So I just go ahead and ask the question, again asked by Dennis in the question and answer forum. Do you consider the occurrence rate of direct links as weight in those networks? If some links have very low or large weights, this might change the final result significantly. So what is your
response? Yeah, so yeah. We do, yes. The short answer is yes. It depends also on the measure that you use. Let me go back to the definitions here. I know they're very formal, which is probably not ideal for presentation, but essentially these two versions do consider the weight. So each link in these two versions of the network is representative of the frequency of transitions. Have I observed very sort of heterogeneous distributions of weights? Definitely. So you do see that all the regions that essentially are covering the locations of fixed points are going to have very high frequency, and also the transitions that they involve, so the links in the network that they're involved in, that they're adjacent to, are also very frequent. And you see certain other regions of state space or the ordinal partition where the weights and the frequency are very low. This does not affect results negatively because this kind of information is sort of as it should, it is representative of the actual dynamics. So when calculating something like the sum of positive Lyapunov exponents using these or these two sort of variants of the network, this kind of information matters, and this heterogeneity in weight matters. When looking for cycles, let's say, or looking to estimate topological entropy, we use the connectivity matrix. And so in this case, these weights do not matter. So it also depends on the kind of observable or the kind of estimator that one is interested in.
Thank you,
Yeah.
Kostas.